topic of my research chair is on subsurface energy data science. And basically, the idea behind this is how to bring data science and machine learning and AI into subsurface energy and developing new tools and more efficient workflows that would help us with various applications that we have in this area. So basically, our goal in our lab is combine machine learning with domain knowledge, subsurface system, geology, geophysics, and reservoir engineering in order to build tools that help in terms of prediction, characterization, and management of these subsurface systems. And of course, in a lot of these, collaboration is needed with experts in various application areas of subsurface. So in terms of areas of interest, so the particular focus for us has been in 3 different areas: description and characterization of complex geological systems, dynamic model updating, and uncertainty quantification is another area that we are interested in, and field development optimization. And in all of this, what we're trying to do is to bring machine learning and AI and integrate that into existing knowledge in these areas in order to develop tools that would be very practical and efficient. And in terms of application areas, we have projects in conventional reservoirs, unconventional reservoirs, geothermal power plants, as well as geological CO2 storage. And this particular last subject, we have heard presentation today, this morning, about CCS and CCUS. And in the past couple of years, almost 2.5 years, we've been putting together an initiative to get a center awarded by NSF. It's a collaboration between USC and Penn State. We call it CO2 Smart. And the idea is basically looking into geologic CO2 storage, modeling, analytics, and risk reduction technologies. And this is part of the NSF program that is called Industry University Cooperative Research Centers. The idea is, under that program, what NSF is trying to do is bringing government, university, and industry together in order to focus on industry needs in different areas, not just this particular application. NSF is a very broad and general organization to support research, basic science research. And in areas where there is an active industry, they would try to focus and support centers that can help address the needs of the industry. And for us, that topic is CO2 Smart. And our kickoff for the center is going to be early next year. So we have 3 posters. 3 of my students are here, Wei, Jodel, and Abir. And they have posters on some of the application areas where we have been leveraging data science and machine learning in order to develop new workflows for subsurface characterization, prediction, and optimization. So the technical presentation. So the topic of my presentation is a PhD work of one of my students who graduated in the summer, Yingxiang. And the idea here is how can we develop data-driven techniques that can be used for CO2 storage monitoring and prediction, and trying to address some of the existing challenges. And today, we saw in the morning presentation, Hadi and Eric, they referred to some of the fundamental challenges in terms of availability of data, the uncertainty that exists in CCS projects. And what we're trying to do is to see, given those challenges, what can data science provide to help us move forward. So if you look at deep learning, which has become very popular and a great interest in various application areas, the main driver of it is really data, right? If you look at if you go deep into these techniques, you will find out that these are really simple optimization techniques with huge amount of data. And if you look at that particular curve on the right-hand side, what you'll see is that around 2012, machine learning literature had reached kind of a plateau in terms of performance until deep learning was introduced, where the performance got substantially improved because the amount of data that was provided to train these models and the size of these models became really large. Now, in our application, CO2 storage, we don't have such data, right? So, we have to see what we can do with what is available. And the solutions so far in the literature are in two forms. We either have to generate data, which means we have to go back to simulators to generate data and train these models, which has pros and cons. The advantage in this case is that you can develop proxy models that are very efficient and bring those, once they're trained, you can bring them online and use them in very complex workflow and increase efficiency. However, the problem here is that there's a need to have a model in place. And number two is that there's a lot of uncertainty. Sometimes we don't trust the models, right? So the best you can do under solution one is really to replicate the model, the simulation model. Second approach is to bring physics in developing the architecture, right? So your deep learning architecture will have some aspects of the physics incorporated in it. And that's where domain knowledge becomes really critical. So if you give it to a computer scientist, they will have a hard time doing this. But reservoir engineers can approach these kind of problems and try to solve them. So in the first approach, basically, there's a simulator that can be used, or many of these models that can be used to generate simulated data. And those data will be fed into a neural network architecture to train that model. It's a black box. And once these are trained, you have to spend some computation time in order to generate the data set. But once they're trained offline, you can bring them online and use them for your application. So the second approach is that you can either start developing architectures that try to mimic some aspects of the physics, so that way you're kind of trying to compensate for lack of data by bringing domain knowledge. Or you can have a hybrid approach where you have simulated data as well as some aspects of the physics incorporated into your architecture. So we have actually looked into, we have ongoing projects on both of these approaches. But one of the things that have motivated what I'm presenting today is limitation in data. And in the case of CCUS or CCS, we have very limited knowledge about the subsurface, right? So if that's the case, how can we proceed? And our objective has been to leverage simulated data, but acknowledge that there is a significant amount of uncertainty. And two is reducing dependence on knowledge about geology. So basically, the main goal of this project was to reduce sensitivity to geological knowledge. And in these architectures that I'm presenting today, we try not to use geological information as an input into a network, which means that once these networks are trained and you take them to the field, measurable data in the field can be used as input in order to do imaging and prediction of the CO2 plume. So that's the objective of this study. So what we want to do, we want to develop a spatial and temporal deep learning models that basically can characterize and predict the evolution of the CO2 plume while reducing the bias from uncertain inputs, and as well as having flexibility to incorporate various types of data. All of this is really needed in this application. So in the offline training, what we do, we try to learn the migration dynamics. So what that means is that we are not interested in a particular geology. We're not interested in particular representation of permeability, porosity, et cetera. But we are interested in learning under different geologic scenarios how the plume evolution or migration takes place. So we're trying to learn that dynamics of the evolution of the CO2 plume. So therefore, and that's basically our emphasis, is that we don't want to have geological parameters as input into our networks, right? And once this is trained, we can bring them online and do prediction based on measurable data from the field. So that's basically our goal. And in this particular example, I'll show one example that from his work, where we have intermittent 4D seismic data, and in between we have some cross-field seismic, sometimes surface kind of cross-sectional seismic, and well data. And the idea is we have two steps. We have one model that tries to use very sparse data in order to reconstruct the existing plume. And there's a second model that actually predicts how that plume is going to evolve. And in all of our predictions, we're focusing on short-range prediction. We are not interested in long-term predictions because those are a lot more challenging to deal with. And our application area is focused on where we are going with this project is doing short-term prediction for monitoring purposes that can be used to optimize the monitoring data acquisition system. So that's basically where we are moving with this project. So we are not doing long-term prediction. Think of this as 2, 3, 4, 5-year predictions, not 100 years prediction. So as I said, step one is having some sparse data. How do you put these together and characterize the relatively high resolution representation of the plume? The second step involves, now that you have the representation of the existing plume in place today, how do you predict it forward and look at a few years from now where the plume would be and how it would expand? And for that, we get the input from our characterization part, reconstruction part, as well as future injection scenarios. Depending on what kind of scenarios you have for your injection, the plume evolution would be different. So I don't want to go into a lot of details in here. Just one point I'll make about this type of architecture. Very standard architectures that rely on encoder-decoders to reduce the size of these problems. And what you see in the middle of this architecture is really the processor, which is really a latent space representation of the input, and evolution of the dynamics is happening within that low-dimensional latent space. Okay, so one thing I mentioned was that we are not using geological input into our architecture. What that means is that our models are trained primarily, solely based on either seismic data, 4D seismic, which will come in the form of saturation of CO2, or in combination with well data, or sometimes cross-field seismic. What we have avoided is no permeability or porosity or those kind of parameters as input into our network, because those are not available, cannot be measured in the field. So here's basically showing an example in which you're looking at very different permeability porosity distributions that we use for training the architecture. Those permeability and porosities are used with very different scenarios for injection of CO2 in order to generate saturation fronts. CO2 saturation, basically plumes, and the plumes are the input data into our architecture, not the permeability, not the porosity. Think of it as we're not interested in permeability and porosity. What we are interested in is under different geological setting, how would the plume evolve? If the network can learn that, then we can bring it online and do predictions with it. So we've tried to stay as close as possible to the type of data that we see in the field in terms of coarsening the data, these are synthetic examples, coarsening the data and making sure that the resolution of the seismic is something that's actually measurable in the field. So those are a little bit of details. So now what we've done, we have looked at various case studies. If you have different interval of seismic data acquisition, 4D seismic data acquisition versus cross-well and well data, what we have basically concluded is that 4D seismic is extremely important in order to get very good performance from these, because those are the 4D seismic offers global data, a good coverage that can be used in order to kind of see the plume and predict its evolution. I'll come back to this because we know 4D seismic is very expensive. CO2 storage is all cost. So we're not going to have 4D seismic, at least not frequently. So So we have to address that too. So these are showing basically performance of different case studies. What you see on the top for prediction and also for characterization and prediction, what you see where the error really grows are the cases where we assume there is no 4D seismic. And that would lead to increase in the error in terms of characterization and prediction. And we have made comparisons with some of the state-of-the-art, which is the RUNet, that has been developed. These kind of models typically assume there is an input about the geology, permeability, and porosity. And we have looked at, okay, what if the permeability was known exactly? What would be the performance? The error would be very, very small in those cases. And if you don't know the permeability and you just take different realization and do prediction under those techniques, then you get significant errors. And what we have seen in our approach is that if you have 4D seismic, your errors are pretty small. But if 4D seismic is not available, then the error can grow as well. And this is an example showing frequency of 4D seismic and how that can result in increasing your error, prediction error. But overall, the method, even though there's no input about the permeability and porosity, has a very good performance compared to the existing techniques. So now, most of the time when you develop these kind of architectures, you want to generalize and go beyond the data that has been seen or under scenarios where things are different, not the same scenarios that you have in your training. So here, what we've done is we have looked at what if the two wells were at different locations. So during training, the location is very different from what we have during the prediction, right? And I'll show you some results about that. The second thing is that what if we don't have 4D seismic because of the cost? What if we had some sparse monitoring schemes where you could actually do cross-sectional seismic, and that's all you could do to reduce cost? And we have basically used cost-effective or sparse monitoring schemes in order to see how the performance will be affected. So generalizing to new scenarios where we have the fixed location, these are our error bars. When we actually randomize the location of the wells, which means that during training and during prediction, the well locations are different, we actually see that the errors grow, but it still are not too bad. So which means that there is some prediction power in the model, even though you have actually changed the setting in terms of well location. And these are basically showing different realizations, different geological realizations. You see this reference model. These are prediction from our models for 1 year with cross-well seismic, 2 year, and 5 year. These are the intervals of cross-well seismic. And overall, the performance has been satisfactory. The second generalization is that when you have a sparse monitoring data, if the cost is high, you're going to have to limit your data acquisition somehow. And one of the ideas out there is you actually do targeted monitoring. So you look at our basically thinking right now is that you follow the plume. You try to basically design your monitoring scheme that follows the plume. That's where the new information comes from. But how do you follow the plume if you don't know where it is? So this ties into our prediction scheme. So you can predict where the plume is moving, and based on that, you can design your monitoring scheme in a very agile and dynamic way. So we have looked at examples with a static monitoring scheme, dynamic monitoring scheme, which means that you extend the scope of monitoring as the plume grows. In the adaptive case, you try to adapt it to the plume evolution, right? So those are the scenarios that we have considered. And what we have basically seen, which is what we could predict, was that this adaptive case performs the best, as long as you can predict where the plume is moving. That's the big if. So this is the architecture, a very similar architecture, except that the training is done assuming you do have a sparse monitoring data set. So there's no 4D seismic, full-scale 4D seismic. So we do have only cross-sectional seismic at different places, depending on the scenarios, whether it's a fixed, evolving, or adaptive. And what we have, these are examples showing basically under the uniform expansion of your monitoring systems, you see that the monitoring schemes, instead of having a full-scale 4D seismic, you will see actually some lines representing seismic data being actually collected within those lines, right, as cross-sectional data. And what we have seen is that the performance generally is okay. It's obviously is not as good as when you have full 4D seismic, but you can still extract meaningful information about the plume location and shape. And when you adapt your monitoring scheme to the evolution of the plume, that's where you get the best result. And this is showing the same basically conclusion using the different error metrics and looking at as you increase the data that is collected, if your monitoring scheme is fixed, which is basically this line, basically as you increase the data collected, the fixed monitoring scheme will give you similar performance as the dynamic one, an adaptive one, but under low or limited data collection, we'll see that the cost stays very low for the dynamic cases, but the performance is still pretty good. So with that, I'll just conclude by saying that, so we've developed what we call CO2 4D net for CO2 storage monitoring, for reconstruction and prediction of the CO2 plume using measurable data in the field. The model is flexible for integrating multiple sources of data, and it's robust in the sense that it's by avoiding geological input into our models. We try to remove that bias. And learning CO2 evolution dynamics is the primary kind of task for these type of networks without relying on directly relying and taking as input the geology. So the extension, we looked into basically if you wanted to extend this for unseen scenarios, well setting at different locations, as well as under a sparse monitoring scheme. And the performance is pretty good. So with that, I will thank you for your attention and invite you for questions.
Thank you, Dr. Jafarpour. A couple of questions online. I'll ask them first. From Matthew Dorcross, how many simulations did you need to train the deep learning algorithms, and how many parameters to be trained in the DL architecture, and how do you make sure that the DL model is not overfitted?
Okay. So yeah, these are very good questions. So when you train this model, all of these are your tuning parameters. How many data do you need in order to get good performance? That's something that you usually play with and do some sensitivity with respect to the data that is needed. In our experience, usually we don't go above 1,000 realizations for saturation data when we train these models. Overfitting is relatively easy to deal with. You try to, while you're training this model, you try to have some validation data set to make sure that the performance stays the same for seen and unseen data before you actually accept the training and the trained model for prediction. What was the other question? There was another.
There's quite a few. I've got to go back. Let's go back. I can't find it now. Let me see. No, this is...
I think it was about the number of parameters in the network. And so I think that's a very good question. Given that there is the relationship between the amount of data that you have and how deep and how large you want to make these networks, so you have to be mindful of that, right? So you can't make these models extremely deep, because what that means is that you have a large number of parameters to train and not much data. And for us, data means simulation in this particular, and a lot of applications that are out there. When we develop these kind of networks, we generate data. It means we run simulations to generate the data. So data is costly, and the cost in here is computation.
Okay, well, now I know the reason why I can't see it, because once it's answered, it moves to the other folder, which is in that big long list. So I wouldn't go back to it. But let me ask a few more questions then. 4D seismic sees only what it sees over time. It does not see, for example, a permeable channel that lies a few hundred meters away from the injection point. where the plume has not reached yet. Do you think not using petrophysical data is a shortcoming? I understand that you mentioned this is only to do prediction over short periods of time.
Right. So obviously with 4D seismic, you will see whatever 4D seismic is showing you. If the plume hasn't reached somewhere, you don't see that in your data. And these networks are, it's not expected even for the networks to predict those. Now, in terms of petrophysics, we are making simplifying assumption in terms of the 4D seismic. We don't go through the rigorous process of inverting for saturation using seismic analysis and seismic inversion. That's one of our future work, where instead of relying on saturation, we want to actually use raw data from seismic to do these kind of imaging and prediction. But anything beyond what the saturation can show, it has to come from somewhere, and that's probably your prior data. If it's not in your prior data, if it's not in your observed monitoring data, then all bets are off.
Okay, question from Dr. Geiger.
Behnam, really nice talk. Thank you. Need to sort of keep fighting the corner for the geoscientists in the room for a moment here. So the two questions that follow up on the previous one. So the first one is, how do you actually ensure that your prior is geologically diverse enough that if you have a channelized fluvial system, for example, that you capture channel geometries, the plume spreading, and with that, the dimension of the plume. And then secondly, you talked about seismics, 4D seismic. You still need some basic information about geosciences to interpret your 4D seismic. So there's a bit of geological knowledge still inherent that you could probably use to your advantage.
Yeah, so that's a very good question, both of them. I think in terms of geology, we are not claiming that we don't need geology, okay? So I showed that the data that is generated is under different geological scenario. What we are saying is that we don't want to assume knowledge of geology. So when we run this model when we bring this model online for prediction, we don't want to provide a permeability or porosity as an input, a geologic description as an input, because we know we can't do that, right?
But your model still, or your prior data still needs to be geologically diverse enough so it captures the difference.
That's a very open question now. So what we show in here is just showing very different, the geological formation stays the same. What changes is the heterogeneity and the variogram that is used for that to represent heterogeneity. So in some of these scenarios, you will see very small scale correlations. In some of them, you will see a very large scale correlation. And then you see anisotropy versus isotropic realization. So in that sense, we have made sure that geologic continuity is very diverse. Now, you can, of course, make it a lot more diverse than this by incorporating other parameters, a structure of the reservoir, faults, all kinds of complex features you can bring in. We haven't done that because for us this is a feasibility study. We just want to keep it manageable. And then once it's successful, we will go toward more general cases. But again, when you do that, it just means that in order to capture the response of all of these geological scenarios, you have to run all these simulations. Yeah. That's the cost you pay.
Thanks.
Yeah.
Okay, so yeah, actually there's a few more questions related to that. How can you get rid of the geologists in the room, right? So
no.
Anyway.
No, we don't.
No, we don't. So let's move on to lunch. Thanks again.
Okay.